Hi, I'm Scott Knockleby. In this video, we're going to look at the inverse velocity solution for planar manipulators. So by the end of this video, you should be able to solve inverse velocity problems for planar manipulators. So we'll again use our Planar 3R manipulator as our example. So for the inverse velocity problem, we want to have a specified velocity of our end effector. This would both be translation and angular velocity of it. And we want to find out what are the joint rates. So theta 1 dot, theta 2 dot, and theta 3 dot. So we'll be given V, which would be x dot, y dot, and alpha dot. And we want to find Q dot, which is theta 1 dot, theta 2 dot, and theta 3 dot for this example. So we already saw from the forward velocity solution that our velocity is equal to the Jacobian, J, times our joint rates, Q dot, right? Where J, our Jacobian for this manipulator, is this matrix here. So we can use this forward velocity. If we just multiply both sides by the inverse of J, we can solve for Q dot. So Q dot is simply going to be J inverse times V. Okay, now this solution assumes that the inverse exists. So a question to ask is, when will there be no solution for Q dot for some arbitrary velocity V? Okay, well, we know from our linear algebra that in order to have an inverse of a matrix, the determinant of it cannot be 0. All right, so if our determinant is equal to 0, all right, we are in what's called a kinematic singularity, or a kinematic singularity exists. All right, so in other words, the equation breaks down. And what happens when our Jacobian determinant is equal to 0, we lose instantaneous motion degree of freedom. All right, so DOF means degree of freedom. All right, will be lost. So in other words, there could be a direction we can no longer move in instantaneously in this singular configuration. And in fact, as you near the singular configuration, you get higher and higher joint rates until at the singular configuration, the manipulator that needs infinite joint rates, which is obviously impossible. So let's make a note of this. So infeasibly high joint rates can be required when we're near a kinematic singularity. Okay, we can use this fact here, when the Jacobian is equal to 0, all right, sorry, our determinant of our Jacobian is equal to 0, to figure out what are those singularities. And so for our example manipulator, right, if we take the determinant of J, so we go back to this matrix here, we take its determinant, okay, and if you do that, you're going to get L1, L2, S2. So for this robot, obviously L1 and L2 aren't 0, all right, but S2 can equal 0. So if S2 is equal to 0, all right, are manipulators in a kinematic singularity. Okay, so if we look at our robot, when S2 is equal to 0, that means link 1 and 2 are collinear. They could either be extended straight out, or L2 could be folded on top of L1. And at that point, we've lost a degree of freedom. In subsequent videos, we're going to look at singularities in more detail, all right, and look at some of the different things that happen near singular configurations.